Hello friends. Today something happened that stopped the semiconductor world in its tracks. South Korea announced that Samsung and SK Hynix will invest $518 billion, that is $518 billion, to build 4 brand new memory chip fabrication plants. It is the single largest chip investment announcement in history. To put that in perspective, it dwarfs the entire US CHIPS Act by a factor of 10. And the reason is not general-purpose memory. It is one specific kind of chip. A chip so critical to AI that entire nations are now racing to control its supply. So in this video, let us find out what HBM actually is, why AI cannot function without it, and why it is reshaping the entire global chip industry from the ground up. Let us start with the basics. Alright, before we get to HBM specifically, you need to understand one idea: the memory hierarchy. Think of it as a pyramid. At the very top sits the CPU or GPU cache, tiny in size but blindingly fast, right next to the processor cores. Below that is DRAM, your main working memory, larger but slower. Then comes SSD storage, bigger still. At the bottom is your hard drive or tape, massive but very slow. For everyday computing, this works fine. But AI workloads are different. A large language model does not just need to store billions of parameters. It needs to move them, continuously, between memory and compute cores. And that is where bandwidth comes in. Bandwidth is how much data you can transfer per second, not how much you can store. When your GPU is asking for data faster than your memory can deliver it, the GPU stalls. It just sits there waiting. That bottleneck has a name: the memory wall. And it is the central problem HBM was built to solve. Here is the interesting part. HBM, which stands for high bandwidth memory, looks almost nothing like the RAM inside your laptop. Standard DDR5 memory modules sit far away from the processor on a flat circuit board. Data has to travel that whole distance through a relatively narrow 64-bit channel. HBM flips that idea on its head. Multiple DRAM dies are stacked vertically, one on top of another, and connected through thousands of microscopic channels called through-silicon vias or TSVs. That whole stack sits right beside the processor on a shared silicon interposer, which is like a dense routing layer that lets data hop between memory and chip over an incredibly wide connection. The result is dramatic. A single NVIDIA Blackwell B300 GPU carries 288 gigabytes of HBM3E memory, delivering 8 terabytes per second of bandwidth. A standard DDR5 system gives you around 100 gigabytes per second. That is an 80-fold difference in how fast data actually moves. The stacking is the secret. Now let us make this concrete. When you run a large language model, your GPU has to load billions of model parameters from memory, process them through its compute cores, and then move on to the next chunk, all during a single inference request. Every time you type a message in a chat app and wait for a response, that process is happening thousands or millions of times per second across a data center. With standard DRAM, the memory simply cannot stream data fast enough. Your GPU cores sit idle, waiting for the next batch of numbers to arrive. That is called being memory bandwidth bound. HBM solves this because its massive parallel connection to the processor keeps the GPU cores continuously fed. NVIDIA's Blackwell B300 GPU carries 288 gigabytes of HBM3E memory built using 12 high stacks, delivering 8 terabytes per second. That is what allows the GPU to stay productive rather than stall. For AI, idle compute cores cost real money, so memory bandwidth is not a nice-to-have feature. It is the whole game. You can see exactly this choice play out in the most talked-about chip announcement of the month. On June 24, 2026, OpenAI and Broadcom unveiled Jalapeno, OpenAI's first custom inference chip. It was built from scratch in just 9 months, specifically designed for running large language models at low latency. OpenAI had a choice: use cheaper standard DRAM or use HBM. They chose HBM. The chip package carries 6 HBM modules surrounding a central compute die. Why? Because serving a frontier language model to millions of users in real time demands that data moves constantly and moves fast. Low latency means every millisecond counts. Standard DRAM would create exactly the bottleneck we described. The OpenAI hardware team put it plainly: the architecture was optimized around memory movement above everything else. Jalapeno proves that even when you design a chip from a blank sheet of paper with cost discipline in mind, the physics of AI inference still point to one answer: HBM is not optional. It is the foundation. Alright, let us pull this all together. The core insight from everything we covered is this: AI performance is not only limited by how fast your processor computes, it is equally limited by how fast your memory can feed that processor. That is what it means to be memory bandwidth bound. HBM solves that constraint with a brilliant physical trick: stacking DRAM dies vertically, connecting them through TSVs, and placing them right beside the chip on a silicon interposer. The result is bandwidths measured in terabytes per second rather than gigabytes. That is why OpenAI chose HBM for Jalapeno. That is why NVIDIA builds every flagship AI GPU around it. And that is why today, South Korea committed $518 billion to build more of it. Memory is no longer background infrastructure. It is a strategic resource that determines who can build the fastest AI systems. Whoever controls HBM supply shapes the pace of AI. Thanks for watching. If you found this useful, hit like and subscribe, and we will see you in the next one.